Alright, so we have critical values x equals 0, 2, and 3. And what we're going to do is put them on a real number line. And we know that at 0 and 3, the derivative was undefined. So I'm going to put question marks there because I don't know what's going on there. I know that the derivative at 2 was 0, so I'll put a 0 there. Okay, so what I'm doing is looking at what's going on with the derivative, and then from that I'm going to glean information what's going on the function. So I have to pick some test values. So your favorite number less than 0, favorite number between 0 and 2, favorite number between 2 and 3, favorite number bigger than 3. And I'm going to check to see if the derivative is positive or negative in there. So when I plug negative 1 into the derivative, I'm going to have a negative on top. The cube root of negative 1 is going to be a negative. And here I'd have a negative. I'm taking the cube root, but then I'm turning around and squaring it. So that factor is positive. In fact, it's always going to be positive. And so this gives me that the first derivative is going to be positive on that interval. When I look at f prime of 1, what's going to change when I plug in f prime at 1? This is still going to be a negative. This, though, is going to change to be a positive. Oops, I'll put that in red there. And as we mentioned before, this factor is always going to be positive. So that means that f prime at 1 is going to be negative. Which means it's going to be negative on this entire interval. Now I'm going to plug in I'm going to find f prime of 2.5. And what's going to change there? The top now is going to become positive. The cube root of 2.5 is positive, and as we mentioned, that guy's always positive, so that's going to be positive. And finally, we plug in 4 to the derivative and see what's going on there. 4 minus 2 is positive. The cube root of 4 is positive, and as we mentioned, this is always positive, so guess what? It's also positive on that interval. Okay, so what's going on with the function f? On the interval from negative infinity to 0, the derivative is positive. That tells us that we're increasing. At 0, we don't know what's going on with the derivative. All right, so we got something weird happening there. But then, whatever happens there, the derivative starts to decrease again, till it gets down to 2. Now at 2, the derivative is 0. That means I have a horizontal tangent line. And then at that point, it starts to pick up again. Something strange happens at 3, but beyond 3, it keeps increasing. Now I look back at my original function f. And my domain here for the original function is all real numbers. So what's happening, even though the derivative doesn't exist at 0 and 3, the function is defined there. So I look at what's happening. And I would say that f is increasing. On which intervals? Well, minus infinity up to 0. And then from 2 to 3 along with 3 to infinity. But since the function f is actually defined there, then it's increasing everywhere from 2 on out. So I can glue those intervals together because f is defined at 3. F is decreasing on the interval 0 to 2. Now, I look at where the function changed from increasing to decreasing. It changed at x equals 0. Is x equals 0 in the domain of the original function? The answer is yes. That means we have a relative extremum there. What kind of extremum? It goes from increasing to decreasing. So we have a relative max at 0, comma f at 0. If I plug in f of 0, I get 0. So relative max at the point 0, 0. And I look at 2 there, and I have it goes from decreasing back to increasing, so it's a relative min at 2 comma f at 2. I plug 2 into this. 2 minus 3 is 1. 1 to the 1/3 power is 1. So I get 2 to the 2/3 power. That's the cube root of 4, if you're interested. Okay? So that'll do it for part A.